Our goal now is to prove that the geodesics on the hyperbolic plane are what we said they were. So there are two cases of the theorem. The theorem said that the geodesics are either straight Euclidean line segments that are vertical, or when the 2 points that we're connecting by a geodesic do not lie on top of each other, then the geodesic is an arc of a Euclidean circle that goes through those 2 points, but is centered on the x-axis. So we're going to talk about that case when Q and P are not on top of each other first. So this is case 1. So we start with these 2 points, P and Q. So P has coordinates x1, y1, and Q has coordinates x2, y2. And the assumption is that x1 is not equal to x2. So that means Q doesn't lie on top of P. And we connect these 2 points by some curve. And the curve is such that, well, it goes from the closed interval AB to the hyperbolic plane, and at the left endpoint of the interval it gives you P, and at the right endpoint of the interval it gives you Q. This other point should be Q. So what will we do? We will show that the length of this curve is always greater than or equal than the length of a Euclidean circle centered at C going through points P and Q. I'm not drawing this circle here. It's sort of right there. Yeah. So that's the Euclidean circle that connects the points P and Q. And the point is to show that the length of this curve, hyperbolic length, is greater than the hyperbolic length of that circle. And I know what the hyperbolic length of that circle is. We have a formula for it. So let's begin with computing the length of this curve. To do this, the easiest thing to do is to actually use a polar coordinate system centered at the point where the Euclidean circle should be centered. So I draw a perpendicular line, I draw a line segment between P and Q, I bisect it, draw a perpendicular ray, and it intersects the x-axis in some point capital C, whose x-coordinate is little c and y-coordinate is 0. Okay, and I introduced a polar system of polar coordinates on the plane, except, normal polar coordinates looks like this. X equals r cosine theta and y equals r sine theta. So now I shift the system a little bit to the left, in this case to the left, so that the center is at 0, at the point C. So I have to compute the distance, or the length of this curve, and the length of the curve, remember, contains both of these derivatives, dx over dt and dy over dt, so I have to compute those. So let's start with that. So dx over dt, I need to use chain rule here. That's a constant. So first product rule, that's dr over dt cosine theta plus r minus sine theta, so that's going to be minus r sine theta d theta over dt. Now let's do dy over dt. That's going to be dr over dt sine theta plus r cosine theta d theta over dt. Okay, we've done this similar exercise when we were trying to derive geodesics on the sphere. So this time I will suppress some of the algebraic computations and just explain them in words, and you can do the details on in your notebooks. So what I need to compute is dx over dt squared plus dy over dt squared. So I need to square this, square that, and add them. So let's look at various parts here, right? Squaring a difference means it's this squared plus that squared plus 2 times this times that, and same here. So this thing squared is dr over dt squared cosine squared theta, and from this expression, I will have dr over dt squared sine squared theta. So because I'm adding them here, cosine squared theta and sine squared theta will give me 1. So from these two terms, I just get dr over dt squared. Now I'm also squaring those two terms. So a similar thing will happen here. That's going to be r squared sine squared d theta over dt squared, r squared cosine squared d theta over dt squared. So when I add them here, the sine squared and the cosine squared will give me 1. So I just get plus r squared d theta over dt squared. And then there are the mixed terms. So here it's going to be minus 2 dr dt cosine theta r sine theta d theta dt. And here it's going to be plus 2 dr dt sine theta r cosine theta d theta over dt. But you see, these terms are exactly the same, so they cancel each other, right? So it's actually everything that I see here multiplied together times 2. And you see I have dr over dt, cosine theta, sine theta, r, and d theta over dt, so they will cancel. So this is that sum. Okay, so how do I then get the distance? Sorry, the length of this curve C. So I get that the length of C that is the integral from a to b, these were the endpoints of my interval, the square root of dx over dt squared, so let me just write this here, plus dy over dt squared divided by y dt. So that's the integral from a to b of that expression over y. I erased y from here. Y was equal to r sine theta. Maybe just so that you have a clear picture of this polar coordinate system, right? I never on this picture drew where theta or where r are. So if you take any point on this curve, let's say here, then the r is the distance to the origin, sorry, not to the origin, to the point C, and theta is that angle, right? So as you move along the curve, you see that the r and the theta change. They are functions of t. And the initial value of theta is alpha, and the final value of theta is beta, because alpha is the angle that this ray forms with the x-axis, and beta is the angle that the CQ forms with the x-axis. Okay, so now note, just like it was in the case of a sphere, everything here is positive, including the sine theta, because my theta is between 0 and pi, and sine of angles between 0 and pi is always positive. So that means if I forget about one of these terms, I get something that is potentially smaller. So I don't need these derivatives anymore. So I get that this is greater than or equal than the integral from a to b. And I'm going to forget about this bit. So I just get this. dt. And if I now take the square root, r is positive, I get the absolute value of d theta over dt over r sine theta dt. So first thing that you notice is that the r's cancel. And secondly, the absolute value of any real number is always greater than or equal than the number without the absolute value. So that's the integral of d theta over dt divided by sine theta dt. And now using a change of variable, changing from the variable t to variable theta, I get that this is just the integral of d theta over sine theta, except I need to change the bounds. When t is a, that means I'm at the point P, so the angle theta is alpha. And when t is B, that means I'm at the point Q, so the angle theta is beta. But what is this? This is the integral we had when we were computing the distance on the length of the Euclidean circle centered somewhere on the x-axis. So this is indeed, I already know these integrals, so this is the natural log of cosecant beta minus cotangent beta divided by cosecant alpha minus cotangent alpha. And this is just the length of the circle, Euclideans of, let's just say, length of E, where E is the Euclidean circle centered at C, passing through P and Q. So what did we just show? We showed that the length of that curve C is always greater than or equal than the length of this Euclidean circle. So any curve that connects P and Q has length greater than or equal than the length of the Euclidean circle. Therefore, the geodesic between P and Q must be the Euclidean circle. Right, so conclusion. Conclusion. If I give the circle a name, oh yes, it has a name, E. E is the geodesic. Is the geodesic between P and Q. Okay, that's actually the harder case of the two. So let's now look at the case where Q lies on top of P. I'm going to keep that formula for the distance up here, but I'm not going to need polar coordinates anymore. This time we're going to use simpler parametrization. We're just going to use the Cartesian coordinates. Okay, so here is again the Euclidean, the hyperbolic plane. And now I take 2 points. Let's say their coordinates are, so this is going to be P, and its coordinates will be x1, y1. And here's Q, and its coordinates are now x1, y2. So this is case 2. Case 2. x1 is equal to x2. So that means I can write these 2 points in this way. So I claim that, so if I connect these with some curve, I claim that the length of this curve is actually greater than or equal than the length of the line segment that connects them. Okay, so let's compute, so let's do the same thing, right? So let this be C, so let's C be a curve connecting, so C from, and this time, so from AB to H, be a curve connecting, so such that C of A is P and C of B is Q. Then I have this formula for the length of that curve. So the length of C, which is given by that formula above, is actually greater than or equal. Again, both of these terms are positive and y is positive, so if I forget one of them, I get something that is smaller. So this time I'm going to forget the dx over dt. Okay, well, you see, that's actually a lot easier than last time. That's the absolute value of dy over dt divided by y dt, which is greater than or equal than a to b dy over dt divided by y dt. Again, change of variable, and this gives you the integral of dy over y. But now, when t was a, then I got p, and p has y coordinate equal to y1. And when t is b, I get q, and q has y coordinate equal to y2. So that is just natural log of y2 divided by y1. And this we know, this is the length of E. Well, what is E now? Where E is the Euclidean line segment joining P and Q. So what did we show again? We showed that the length of that curve C here is always greater than or equal than the length of a line segment that connects them. So the line segment is the geodesic. Between P and Q. Okay, so this proves our theorem that there are two types of geodesics on the hyperbolic plane. Namely, if one point lies on top of the other, that's just a straight Euclidean line segment between these 2 points. And if the points do not lie on top of each other, you just find a circle, Euclidean circle, whose center is on the x-axis that passes through those 2 points. And the arc of that Euclidean circle between those 2 points gives you the geodesic between them.